90 classmates. My name is Peter Courier, and we'll be having a look into nonlinear dynamics and chaotic theory because my topic is memristors, the missing circuit element, and memristive systems and circuits. First I'll talk about what a memristor is, and then I'll talk about the process, how it works, and then I'll conclude with future applications and how the memristor can be used. So what is a memristor? Well, in the electrical engineering world, it's any two-terminal element that exhibits a well-defined curve in flux versus charge, the time integrals of voltage and current, respectively, or current and voltage. If you compare a resistor to a memristor, well, you know that a memristor, since it's a basic circuit element, it's a passive element which does not take energy from the circuit. That's what a basic circuit element is. So a resistor, you can think of it as, if you were to use the water analogy, you could say that the resistor is like a tube where if you put water through it, depending on how thick it is, that's how much that it kind of governs how fast the water moves through the tube, right? Depending on how much water you put in it. A memristor you can think of as like a tube, but it adjusts the thickness of it as you put more water into it, or it changes its size depending on how much water there is. So the HP Labs actually built a working prototype of this, and this is a picture of it. It was taken using an atomic microscope. It's made out of titanium dioxide. There's an array of I think 17 of them. Each one is about 50 nanometers thick, and it's 2 layers of titanium dioxide. And well, they built it with help from Berkeley and Stanford and a bunch of other researchers as well. The actual theory behind it was, the memristor was actually discovered first by Professor Leon Shaw, and he's a professor here in the EECS department at Berkeley. I had an interview with him, and this is how it works. It's very, very complicated stuff, so I'll just gloss over a little bit. You see that there's a nonlinearity when you add the memristor to a basic circuit using, the basic circuit elements. There's only 3, but now that there's 4, it's actually a new element. There used to be only 3, and now there's 4. And when you use it, it adds a nonlinearity to the circuit, making a chaotic IV curves. These are actually these are real things that happen in our natural physical world, and it's very very fascinating, very beautiful to watch. The IV curve for this diode, it's actually an ad hoc memristor that Troy used to exemplify this behavior. It has nonlinear resistance. See, as you get closer to the origin, the resistance increases. A real memristor will have sort of this behavior, except it'll look like a figure 8, sort of, or sinusoidal. But it causes these void zones here, here, and here, because it crosses the I equals minus V line in 3 spots. And anything that has this kind of behavior, where it crosses this line, will create something of this shape. It's called the double scroll, and you'll see that it's very unpredictable because you don't know where you're going to be in this cloud of sort of a random. It could be at any time. You could be anywhere in this shape, but it's a control. It's bounded, and so you know you're going to be in here, but there's infinitely many points where you can be, and well, that means it's unpredictable, which means you can't really say where it's going to be, and it's also got very sensitive dependence on initial conditions. Initial conditions here are the alpha and the beta, which if you change the value of these resistors and capacitors, you'll change the initial conditions and get a completely different shape. So the way you can use these now is they can be used for non-volatile memory, which is like a flash drive, except flash drives today use transistors and stuff like that. Using a memristor in a flash drive is not only cheaper, it's faster, and also you can, you know, make computers with memristors in them and use them as memory. The way you do that now is like, well, your computer right now uses DRAM, which whenever you turn off your computer, all of the DRAM gets erased. You won't have to do that with memristors in your computer anymore, because memristors, they sort of remember the state that they were in when you take power out, or when you turn off the power. So basically, if I took the battery out of my computer right now, it would just turn off, right? But if it had memristors in it, you wouldn't have to wait for it to boot all the way back up again, taking all that energy and power to go through the whole boot process. It would still be in that state where when I turn it off, it'll just bring this screen back up again. Like a lamp, if I just turn it off and turn it on, nothing will change. So another future application would be artificial intelligence, because these circuits kind of act like a neuron. It's like they'll simulate the human brain or any like organism brain, where it learns, it remembers, and it reacts. And using these in our circuits will, in fact, make machines more intelligent in the future.
Sorry.
Thanks. Questions? Timothy?
Well, so you say that memristors are unpredictable, but at the same time you said that they can be used as memory. But as far as I know, memory has a very, at least most of its states are clearly defined, because that's how we store and actually load from memory elements. So how does that work with memristors? Do you know?
Well, the way you put a memristor in a certain state is you give it some current, and then it'll have that. It'll have a value for however resistive it is. You can use that value to store data. Yeah.
So how does the shade has to do with this kind of loss with it?
Well, these are bifurcations of these three differential equations, and since there's a nonlinear term here, it's a chaotic system. This nonlinear term comes from this. So basically, x is the voltage, and you plug in x to this, and you get a number, and that depends on this, which also changes these values and makes this chaotic system.